I'm Minsu, and I'll be reviewing the paper, The Anatomy of the Facebook Social Graph today. If you haven't already seen the class lecture for today, I recommend that you do that first before looking at this presentation because the lecture goes over some important concepts that you need to know to understand the results in this paper. It may seem like an obvious question, but I like to start by asking, what actually are graphs? Here are some examples of graph structured data that we might encounter in the world. Here's a molecular network. This one here is a subway network. This is the entire Facebook graph visualized on a map of the world. And this is a visualization of a brain connectome. So as you can see, all four of these cases, the data is represented by having some sort of node and connections between those nodes. Let's make some example nodes here. And these have connections between each other. So in all four of these examples, it actually matters how you arrange the nodes and connect them. So let's take the molecular network for example. It actually matters that you have this structure in this exact configuration, and it's not enough to say that you simply have a list of some molecules. You actually want to know the exact structure that they're arranged in. And so, if you wonder how much can the structure of a graph really matter, it's easy to demonstrate that the structure of the graph really does matter. Both of these cases show that even if you have the same set of nodes, the way that you arrange them will decide what characteristics they get to have. So, in the case of the top example, you have the same set of 10 nodes representing, let's say, 10 people connected in very different ways. In the first one, we have just groups of 2 or 3 people connected to each other, and there aren't any connections between the groups. And in the second case, everyone is pretty much connected to everybody else. And in the third case, it's a mixture of the first two with there being some clusters but with all of the clusters having at least one connection between each other, like here. So as an example, let's say that these are 3 groups of 10 people trying to come up with a new invention, right? Then in the first case, if let's say this person comes up with a good idea, we would like the idea to be passed on to these other groups for further discussion, but that cannot happen because there are no edges connecting these disparate groups. In the second case, let's say a similar person has a good idea. In this case, it'll definitely get propagated because the entire group is so fully connected. But because it's so fully connected, we may have an issue that after we get that one idea, that idea will just keep self-circulating and it'll prevent let's say, this guy from having a better idea. In the third case, it's arguably the best balance of the two, because this guy could have a good idea and it'll get passed on, but because there aren't too many edges connecting everyone to everyone else, we won't have that same problem of the same idea circulating too much. And briefly, for the second example of the molecules, we can see that the way they're connected actually determines like what kind of molecule they are. So as we can see, the defining characteristic of a graph is the way that the vertices of the graph are connected to each other, how many connections they have, and which other vertices they're connected to. So the central feature that we want to know in a graph is going to be the connection between any given vertex and other vertices, and those are called edges. And so for any vertex, we want to at least know the number of edges it has. So the term for that number is the node degree, and it's simply the number of edges connected to a node. So in this simple friend network, Brenda has a degree of 4, Bill has a degree of 2, Becky has a degree of 3, and Ted has a degree of 1. And now we're ready to see the actual results of the paper. The paper analyzes the entirety of the Facebook social graph. And to begin with, they calculate the degree statistic that we saw from before for every user or node in the entire Facebook graph. So let's look at the axes first. On the x-axis is the node degree, and on the y-axis is the fraction that the corresponding node degree accounts for. I want to quickly mention that the graphs we'll see from here on are on a log-log scale, which means that the x-axis and the y-axis are both on a log scale instead of a linear scale. So what does that mean? So to see what that means, I plotted y over x squared on the regular linear scale and on the log-log scale. And you can see that on a regular scale, you see this exponentially decreasing curve, but the same graph on the log-log scale becomes a straight line. And that's the key property of the log-log scale, that equations of this exponential form appear as straight lines. And if you recall in the lecture, the degree distributions of many social networks can look exactly like this because they follow a power law of this form. And so if the degree distribution of Facebook's social network followed the same power law, we would expect to see a degree distribution graph that looked like this, which would translate to a straight downwards line in the log-log scale. And in the graph, we'll see that it doesn't exactly look like a straight line. So with the log-log scale in mind, we can analyze this degree distribution graph. So on the left is a simple distribution that shows what fraction of users have a certain node degree. So on the left graph is a simple distribution, and on the right is a cumulative distribution. So starting with the left graph, the fractionally largest group is actually the users who have one friend, represented by node degree of 1. And since this mark here is 1 over 100, corresponding to 1%. The users with one friend account for a little bit over 1%, maybe 5. And as the number of friends or the node degree increases, we can see that the fraction decreases. But there's a limit to what the left graph can tell us, because the statistic is calculated for an exact number of node degrees, meaning that users with, let's say, 49 friends are treated separately from the users who have 50 friends, as two separate numbers. So the cumulative distribution on the right addresses this issue. The y value at degree k, let's say 5, measures the fraction of users who have degree k or higher. So at x equals 5 or k equals 5, the cumulative distribution value is close to 100, which means that the majority of users have a degree of 5 or greater. If we go up to, say, 200 friends, which would be around here maybe, the corresponding cumulative distribution value would be roughly in the range of 20%, which means that only 20% of users have a degree of 200 or greater. So the paper tells us that most individuals have around this number of friends, 200 or less. And they actually calculate the median count of friends as well, and that turns out to be 99. And finally, I said that if the degree distribution follows a power law, we would expect to see a graph that looked like this. But we can see that it doesn't exactly have that shape. It has this hump in the middle part, maybe corresponding to degree 50 to 500. But regardless, the paper points out that we can still identify this hub on the right part of the graph, which is users who account for a very small fraction of the overall graph, but have very high node degrees. The graph ends at 5,000 because that's the maximum number of friends that Facebook allows, and these users are the ones who have close to the maximum number of friends. So the graph confirms that the Facebook graph also exhibits this common feature in social networks called the hub. So we've covered the basic degree distribution for the Facebook social graph. And now moving on from degrees, because nodes are connected to each other with edges, we can try to find out what kind of paths these edges form throughout the graph over multiple vertices. And one of the more interesting questions that we can ask is, what does the average path look like? Are they short or long? If we can measure the lengths of all the paths in the graph, what does the distribution look like? So to do this, we can define a simple function called the neighborhood function. And it's just going to be a simple count of the number of vertex pairs that are reachable from one vertex to the other in h edges or less. Each edge in the path here is often called a hop. So the number of vertex pairs So on the graph, the y-axis is the percentage of user pairs that are within h hops of each other. So starting with 0 hops, obviously this number is going to be 0. And up to 2 hops, the percentage of users that you can reach within 2 hops is very low. But once you reach 3 hops, going upwards to 4 hops, the percentage starts increasing dramatically. From a different perspective, 3 hops or 4 hops, somewhere in between, would be the point where you start reaching exponentially many more people. So let's say, let's draw. Let's say the graph sort of has this cone-like structure. Within 1 or 2 hops, you would reach very few people. But once you start reaching paths of length 3 or 4, you begin to reach exponentially many more people. And we can see that in the graph, by 5 hops, the exponential growth is to the point where it covers basically the entire graph. So it seems to be about 90% of the entire graph. And note that this is not on a log scale. And by 6 hops, it's at over 99.5%. And if you recall the 6 degrees of separation experiment by Stanley Milgram, they basically did this same experiment in the real world, or the physical world, and found the same results. So the results here confirm the same, that you can reach pretty much anyone in 6 hops or less. Before we move on to the next result, which deals with connected components, I should mention that the conclusion in this section that the network has short average path lengths relies on an important assumption. And that assumption is that a path exists between most pairs of vertices. And to see why this is, so let's imagine that for the Facebook social graph, the entire graph looks like this, but there are 3 large disconnected sets of vertices which are connected internally but not with each other. So if it's false that a path exists between all pairs of vertices, that these paths don't exist, then we could be in a situation where the 6 degrees of separation only holds within each disconnected part of the graph. In which case, it wouldn't be correct to say that you can reach any vertex within 6 degrees of separation, or 6 hops. But fortunately, we can confirm that this is not the case for the Facebook social graph, and we'll see this next. Actually, the connected component is quite simple to define. Connected component of the social network is, just as the name would imply, it's a set of nodes in which each pair of individuals are connected by at least one path through the network. So it's actually exactly what we've drawn up here. This graph without these paths would have 3 connected components. But unlike this graph, if a graph has a connected component that spans the entire graph, or most of it, so then we can use the same neighborhood function from before to describe the diameter of a graph. Here the diameter would be 3, which is the longest possible path. And the diameter is just the maximum distance between any pair of vertices in the graph. Which incidentally we would know if we calculated the neighborhood function NH from before, since we would have been counting the number of all paths of length h, whatever that h may be. And so the diameter would be simply the maximum h. That was found. So now let's look at the graph. We're in the log scale again. And the authors tell us that if we look at this second largest connected component, it has just over 2,000 individuals or nodes. Whereas the largest connected component, the outlier all the way over here, consists of 99.91% of the network. So this component comprises the vast majority of Facebook users with at least one friend. So our previous conclusions that the average path lengths are short and that you can reach almost anyone within 6 degrees. Hold for the entire graph. So if things like the path lengths and component structure give us a macroscopic view of the network, clustering coefficients and degeneracy are more local properties of the network. But before we can calculate the clustering coefficient, we need to know the neighborhood graph, which has the same word neighborhood as before, but it's actually quite different. This time the neighborhood of a user is the friends of the user, so actually the same definition that we used for calculating the node degree width earlier. The neighborhood graph is also known by other names like the eagle graph or the one ball. And these are quite intuitive because if we take this small graph, for example, the whole network is here on the left. So a neighborhood graph defined for this graph for, let's say, user 3, also known as 3's eagle network, would be here. Since the subgraph includes only the eagle and his friends. Actually, the neighborhood graph does not include the eagle, so the precise definition that this paper uses is this one. With the neighborhood graph defined, we can compute the clustering coefficient. The clustering coefficient can be viewed as the number of actual friendships that exist and the number of all possible friendships that could exist within the neighborhood graph. So the actual friendships are just going to be counted depending on the edges that exist. And for all possible friendships, we need to calculate the value. So it's the same as counting the combinations of picking two friends to be friends with each other out of k friends and without overlap. And from probability, we know that that equals k choose 2, which is k factorial divided by the product of k minus 2 factorial and 2 factorial, which is just equal to k times k minus 1 over 2. In this example, if we count the number of all possible friendships, let's list the nodes. They are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, 5, 6. So that's the total number of all possible friendships and how many actually exist for user 3. It's 1 and 2. For user 5, it would be just this one. Oh, and this actually should be 1, 2, 5, 4. Not 1, 2, 3, 4. But the result is the same. So now we'll look at the graph of the average clustering coefficient. So this graph is produced by calculating the clustering coefficient for all nodes of a given degree. So there are many nodes in the graph that have a degree of 5 and 6 and 7 and so on. So they calculated the clustering coefficient for all of those nodes, and for a given degree number, node degree, they took the average of the clustering coefficients. And since it is a distribution, not a single number, they also show the 5 and 95th percentiles with the dashed lines, but we'll focus on the mean value. So starting at degree 2, if we calculate the maximum possible friendships, it's, if you have 2 friends, you could have 1 friendship, or 2 times 1 over 2 and so on. So that means that half of all such users have a friend and the other half doesn't. So that seems like a pretty decent sized number. And for 5, it's slightly less, but it's still quite high at maybe 0.3 or something like that. If we go up to the users with say 100 friends, which is where the bulk of the users will be, the average local clustering coefficient is still roughly 0.15, which indicates that for a median user, 14% of all their friend pairs are themselves friends. So if we plug in k equals 100 to the all possible friendships equation of 100 times 99 over 2, and this was 4. And 14% of this is 693. So 693 pairs of unique friendships between 100 friends seems like a pretty high number to me. And if we look further in the graph, the clustering coefficient gets smaller as you have more friends, so there's a downward trend. But this seems natural for a variety of reasons, and the authors say that it's also consistent with other studies. At 5,000 friends, the clustering coefficient drops sharply, indicating that these users are friending users more indiscriminately. So they're probably more likely to friend strangers on Facebook. Qualitatively, I think these results make sense because, well, at least when I was using Facebook, my friending activity was mostly based on the people I'd met in real life. So colleagues, coworkers, and other socially proximal people were likely to be added, at least for myself. And it would make sense that such people would know each other too. So we've covered clustering, but you'll notice that on the right is a figure that displays the average degeneracy. Because degeneracy isn't a concept that we've covered in class yet, I'll just briefly summarize what the paper's findings are. So degeneracy basically is a measure of sparsity or density, which is the same thing except in an opposite direction, I suppose. So formally, degeneracy of an undirected graph is the largest k for which the graph has a non-empty k-core, and the k-core is the maximal subgraph of G in which all vertices have degree at least k. So as a simple illustration, this is a 3-core of this graph, and all the vertices in this 3-core have degree 3. So that means that for a high value of degeneracy, the largest non-empty k-core has a high number of vertices. So I think we can take that to mean that the graph will have densely connected parts within it. So according to the authors, the degeneracy values seen here are quite high. So the Facebook graph's neighborhoods are very dense based on these degeneracy values. For example, for a user with 100 friends, the average degeneracy of their neighborhood is 15. And for users with 500 friends, the average degeneracy is 53. This means that they have at least 54 friends who all know 53 of their other friends, and the authors say that this is more dense than other social and non-social networks they compare to. So the Facebook graph is sparse as a whole, but when users accumulate sizable friend counts, their friendships are not indiscriminate at all, and instead center around sizable, dense clusters of users. Finally, there are a few results in the paper that I haven't covered, but since some of those concepts are ones we haven't covered yet in class, and in the interest of time, I'll end my presentation here. So in conclusion, By analyzing the degree distribution of the Facebook social network, we learned that pure power law was not quite accurate to describe the degree distribution of Facebook, but we were able to confirm that hubs are definitely present. And through analyzing the paths of the graph, we also confirmed the small world effect and the 6 degrees of separation phenomenon on a global scale, with the average distance between vertices being 4.7 hops. And finally, through analyzing the clustering and degeneracy values, we found that the Facebook social network is nearly fully connected, has short average path lengths, and high clustering. That's the end of this paper review. I hope it was useful, and thank you.